three concrete classes. The problem with this approach was that it required users to create these wrapper types and create these wrapper types anytime they wanted to do the interchange, which also held potential perf problems with the additional allocations that were being made, and that they may have been exposing more operations than the native tensor types were actually supporting.
But why? What do you mean by they had to create the wrapper types? Could they use the abstraction?
They had to instantiate an instance of one of the concrete wrappers.
Why not implement their own abstraction?
Because then you can't interchange it with anything taking the concrete. So
it will never be true, no matter what we do. If you take a concrete type, then you're not gonna interchange.
Right, but the point of the interchange types is on interchange boundaries you would be able to take the interchange type instead.
Yeah, why is the abstract class not interchange?
It was an interchange type. The problem was that in order to instantiate the wrapper type, you had to create a new instance, like a dense tensor, and then pass the underlying native buffer into it.
You didn't have to, but there were valuable abstractions in these concrete types as well. So the base type was just about multi-dimensional access, and then the dense tensor, it was a concrete type, but it also exposed the concept of a dense memory layout, and that in particular is interesting from some consumers. So, I think we were in the experiment, and the whole concrete type versus interface thing was really still something that was up in the air for us. It was like a hallway conversation with MO that caused me to go down one path, and we were going to wait and see how things landed. As we started seeing people adopt this, they all were trying to, the concrete types weren't good enough for them to just directly use.
I totally understand that.
Yeah.
I'm just asking what's wrong with the abstraction. We already have an abstract tensor type. What's wrong with it?
You have to, it creates an additional layer of abstraction that requires them to either pass it into a heap allocated object. So a lot of the times the tensor types in these libraries are struct types. So you can't just inherit from the abstract base class. You have to actually create one of the concrete implementations of that inherit from the abstract class, wrap the memory in it, and then potentially add additional operation support for the native library to get everything working. So you end up duplicating a lot of the logic that's already on the concrete tensor type for that library.
So basically what you are saying, what's wrong with the abstract tensor type is that it cannot be implemented by structs.
That's part of the problem.
Well, I mean, but you still end up boxing, right? As soon as, unless everybody takes it T where T is I-tensor of something, right?
Right. You'll still end up with a potential box in some scenarios. You can mitigate some of that with generic specialization and other runtime tricks. But the biggest part of one of the biggest issues is that you end up having to. Many of these tensor types have very specific behaviors and optimizations that can be done for the underlying layout of the tensor type for that library. The abstract class mechanism requires, in order to get those optimizations, you then have to extend the abstract type yourself, and then re-implement all the logic you've already implemented on your tensor type.
Maybe I'm slow, but I still don't understand how this has anything to do with interface versus abstract class, because somebody still has to map whatever is on the interface to whatever the underlying plumbing is, or whether you inherit from a base type and you override methods, or whether you implement an interface and implement the method. Somebody has to do the plumbing.
Right. But when you have the interface, you can minimize the amount of duplication you're having to do.
I minimize the amount of what?
Duplication. You could just forward to the existing method because you don't have any existing definition for that an abstract class may have, or behaviors that an abstract class may have already.
Does it have behaviors?
The abstract class had some minimal behavior, and then the dense tensor that we shipped that inherited from also had their own behaviors that were not always applicable.
We were trying to handle the linearization of indices for people.
And so if it's just behavior, can we make the method virtual and then people can change their behavior? It is virtual.
Yeah, they were virtual.
I have to say I'm still not understanding. Like, we have an abstraction. The only thing that I understand is if people want to implement it on structs, it cannot. That's the only thing that I understand.
We shouldn't be really looking at this as... So we shouldn't be looking at this as change from what we already have, because we haven't really shipped a fully ratified. So we should be looking as two equal alternatives.
Yeah.
And rather than, like, say, counting anything against this approach because it's a change from what we have.
So the tensors that we shipped are not stable?
We've not shipped them.
We've branded them as pre-release, same as ML.NET.
Oh, okay. I see.
Yeah.
So
Right,
this would
V.
basically...
1.
This is assuming we are basically starting a review. We are about to add tensors as stable to the platform. What should they be? Is that how we should see it?
Yeah, that's how we should see it.
I see. Okay, so then my question is, why not just ship a solid abstract class or maybe set of classes? But let's, like, why are the interfaces?
The interface allows you to, on the existing types you've already exposed, pass them around directly and still allow type checks and everything else without having to add another layer of abstraction.
And so people have existing implementations of something like a tensor?
Yes, every single library has their own existing implementation of tensor that generally wraps the native library's implementation.
Yeah, that's the same problem that Rosa had with their symbol APIs, right? If you have basically multiple hierarchies, so it's basically the trick we're doing with a hierarchy where we have different shapes is what other libraries already do as well. So they have whatever hierarchy they have, right? And so it's pretty hard in a hierarchy situation to say, here's our hierarchy, here's your hierarchy, reconcile that, because you basically, at that point it becomes...
Yeah.
So
I think the Torch Sharp has or had this problem, right? And maybe Matteo can jump in on this, but when we tried to put Tensor, the base class, into Torch Sharp, like there was pushback into putting it into the Torch Sharp base library, and instead it got added to a separate library that then wrapped that underlying Tensor class.
And what was the pushback?
I think it was because we want to have the really thin layer on top of torch tensors that basically contain only the pointer and have no dependency.
Yeah.
Because if we use no other dependency between that. Yeah.
And what do you consider a dependency?
This library.
Like memory or now with if we use the system numeric tensor, I think that we have dependency to to the SNT, to memory, etc.
But if you have dependency on these interfaces, you cannot have dependency to memory. These interfaces don't solve your problem of dependency.
I was not the one that did this pushback. It was Miguel. So I wanted to also have the SNT directly into our representation of tensors instead of having two different representations. But
my goal initially with the types was to make it so that the types were directly usable as an exchange type to wrap the native memory. So that was initially my thought, was that people wouldn't need to even define their own types, that they could write an interop shim that would directly get the data from a native layer and wrap this. Yeah. But it hasn't panned out that way, because folks want to do more with these objects than just represent the data behind the tensor. So they also want to expose operands and methods that are natively provided by the tensor library. So like Torch has, and so they want objects, and so our dense tensor and our sparse tensor is never going to give them that, because they can't, like, we have a set of, like, basically the decision that is access a read or is it a p invoke, right? Some people might actually want to make that decision themselves as opposed to have us.
Still, it has nothing to do with class versus interface.
You also lose the type information when you use a class. If you have a struct and you have to wrap it into a class, you have lost the type information of the underlying type. So you can no longer say, if iTensor is Tensor Flow Tensor,
Right.
then cast it to Tensor Flow Tensor and operate it as a Tensor Flow Tensor. Interface provides abstraction like the class does, but it maintains the underlying type information of the original type.
Yeah, I was not proposing. I'm not proposing that people wrap.
Right, and allows you to perform tricks like generic specialization to remove the runtime cost of the boxing or.
So do people, any of these tensors that we are discussing, the third-party tensors, are they structs?
Yes.
Any of them?
Yes.
Really?
Yes, because most of the time they are just a wrapper over native memory.
Which one is it? I looked at libtorch, that's a class, and Onyx is a class. Is it TensorFlow Sharp?
Yes. So in TensorFlow Sharp, we had the class initially, but now I have a new version with struct that is 2 times faster. So I think we're going with struct.
So the problem with struct, so we had these interfaces. Now the struct would implement the interface, and now we literally are forced to either implement the generic specialization trick or box every time.
Or you can box and also rely on the runtime optimizations for devirtualization, speculative devirtualization, which is partially existent in Netcore 3 and will continue to be improved in future releases. There's a lot of things that...
Well, the box is allocated anyway. The moment you call box is allocated. You need to virtualize, but...
And boxes are also being worked on to become struct allocations rather than heap allocations. So the cost of it is mitigated and becomes non-existent.
Honestly, my concern is not perf. My concern is just if you look at these APIs, they are not what I would consider simple, right? Like, they are more like, I mean, they're simple in the sense that we try to get them down to some small number, right? But compare this to, let's say, comparable ID removal, which is fundamentally simple and very unlikely to change, right? Those are things where I can totally see us eventually wanting to add a method. And then with interfaces, you're effectively fucked. Like, you can, like with DIMs, we may be able to add one, right? We may be able to do things with extension methods, but it will be very hard to evolve these abstractions as soon as you settle on interfaces. And that's honestly my biggest concern with this is being interfaces.
The reason why these methods were chosen is because they represent what is essentially a bare bones tensor across all of the native libraries that expose tensor types.
Yeah, I don't doubt that this is what we think is the primitive, right? That's true for any abstraction we ship, right? But like, you know, when we looked at stream in V1, it looked perfect, right? But eventually you add a new cross-cutting concept, and then, I don't know, maybe it like takes span, right? I mean, originally we may have exposed arrays, now we're exposing spans, right? So you can easily imagine us eventually wanting to add another method that types can subset, and then the only way to do it is by basically adding a new interface, deriving from the existing one, and then basically everybody who uses these interfaces now has to write fairly ugly code because you basically have to do type checks everywhere. And that's, I think, the problem with the interface method approach. Like, if we go with this approach, I mean, I understand that it's easier to basically enlighten existing libraries with these APIs because all you have to do is implement them on your existing types, but it will make it fairly hard for us to evolve tensors over time. And I think that, so the question I think from our end is, this is a new exchange type, right? So every time you introduce a new exchange type, you will have this problem that existing libraries who didn't take a dependency on the exchange type are harder to evolve. They can either add a breaking change to their libraries, or they can just add new overloads to take our types, right? But I think fundamentally, like, it's very hard to basically, change the exchange currency without being a breaking change.
Right.
I think that's fundamentally a problem.
One of the other problems with the interface versus classes is that none of these libraries are writing these tensor types as C# owned memory. They're all writing them as native owned memory that interop with a underlying native library,
Which is fine.
And so you're going to have additional cost of abstraction whether we do class or interface, and none of these libraries, because they're native, agree necessarily, other than a few base methods, what a tensor is and what's available to it. Not all of them expose operations. Some of them just expose views and slicing and reshaping.
Yeah, you're basically saying most of them exist in native land, and so the question is how much overhead we want to inflict on the managed side to point to it, right? And I think you could argue that interfaces with better devirtualization and boxing behavior would basically become a zero overhead abstraction, but that's also
it's not just that. It's also even if we were to expose classes, we would end up trimming it down to this much. And
sure.
And if we expose new methods, the default implementation for those methods is basically throw not implemented, because not every library guarantees that a given operation is available. And since it is existent in native memory, you can't definitely say whether something's readable or writable, or that you can even create a new tensor, because it could be a managed call.
Well, I mean, we could implement a very bad version, right? We could always clone. Like, if these are the base abstracts, then we could always envision a implementation that uses these methods to copy everything to managed memory, and then we could do whatever we wanted. And in fact, that's like, if you look at some of the base, like some of the stuff that I was putting in the base dense tensor, it was that. It was like, sure, we can limp along and do these arithmetic operations, but you'd never want to use our implementation because it does like really bad stuff.
And that basically drives the user into a pit of failure, because if you're in torch sharp, for example, you're going to want to have a torch sharp tensor basically the entire way through. And users are going to be able to accidentally do operations that return a managed tensor that you then need to rematerialize as a native tensor, and you're killing perf.
What do you need to make? I don't understand. Somebody implements, so let's say they abstract, they have exactly same shape, they are just abstract classes, right?
Yes.
And then they don't have operations that are...
No, and then in the future we extend it to add operations.
With what?
If in the future we extend it to add operations, which was Immo's question about doing interfaces, how do we extend it in the future?
But there may be something, like we have another, let's say we want to add an indexer that takes range. What do we do in the future?
Yeah. That's what I mean by cross-cutting things, but it doesn't necessarily
so those types of changes we would benefit from an abstract class.
Exactly. That's my whole point.
Or we address it with DIMS, which is supposed to be coming eventually.
But DIMS.
But as soon as you do DIMS, then any platform that doesn't support them, you can't use the library on anymore, right?
Yeah, you're
right,
really done
but you also can't do that if you want to support something like range.
Right, but I think my point is more about, if you look at Stream, right? If you look at the additions over that Stream in V1 basically had both synchronous and asynchronous APIs. That's still true today. It's just that the way we modeled asynchronous APIs have changed, right? And same with indexers, right? We now have a range or index-based indexer. Like, it fundamentally doesn't change the type. All it does, it makes some things more easy to use, and those are things that are harder to evolve. But I don't know how we fix that.
We have guidelines. The guidelines say the following: unless you need to multiple inherit, don't use interfaces, use abstract classes. We can keep discussing the guideline, or we can kind of think whether multiple inheritance is required here.
Yeah, so I think he has one point, though, which is basically, if you think of existing libraries like Tensor Flow, given the way tensors work, pretty much everybody has some notion of a hierarchy, right? And so the thing is, in that sense, it's multiple inheritance if you ask them to marry ours with theirs.
Not necessarily.
Yeah,
the only
because-
reason, even if they have a hierarchy, the only problem would be if they cannot put this type at the top.
Well,
But we have multiple types. That's the problem.
yeah. So
What?
let's
We
say
have
that
multiple types. Like we have an abstract
So,
I-tensor.
yeah, if they basically they cannot put one of these types at the top of the hierarchy.
right. So if they have a tensor type and they have a dense tensor type which inherits from their tensor type, they're already broken because now they can't inherit from our dense tensor type.
Correct. Is that the case?
And I'm not sure of the particular cases in the libraries today. I've not looked super closely at Onyx, but the places that are using structs already can't inherit, so they're also broken.
But as we just discussed,
Right.
supposedly there's not even one that today has structs and one is thinking about moving to structs.
Because it's 2 times faster.
Could I ask a question about this? Sorry to break in. Wouldn't a more natural way to, if this is an exchange type, couldn't libraries just continue using their own types? And if they want to have this sort of thing have an implementation that wraps around it, rather than injecting it into their own type system? Why are we talking about that?
Because
Why do they have to descend from this thing to use tensors in their own?
the existing implementation prior to this proposal is a wrapper type, and that's turned out very poorly. It also ends up losing the type information of the original tensor type.
Okay, but I mean, if I were to sort of look at this and say, is this a suitable replacement for VBuffer, for example? My answer to that would be no, because it will result in, I mean, it may be that the existing wrapper type didn't work, but I don't know that I would want this either.
Right. This isn't supposed to be a drop-in replacement for the type. Most of the time, a library will be operating on exclusively their type. But once you get to higher libraries that want to support both Port Sharp and Onyx, for example, you end up needing, they either have to implement both or they need an interchange type that allows them to determine what the original type is and what to do to support both libraries.
Okay. In which case, it strikes me that a wrapping type would work, but you said that doesn't work. Do we have a document somewhere describing the difficulties with that, so I don't waste too much of your time?
I don't have a write-up on GitHub anywhere right now. I've got a lot of email notes from previous meetings where we've discussed it, though.
Okay, all right.
I think the general problem with wrapper types is also that unless you're very careful, it can easily result in allocating a ton of objects that are basically immediately becoming garbage. Then you have your library is exchanging with some other library and you're passing tensors back and forth, right? Then you basically have to find creative ways to do that, which we have done in the past too, but it's not easy to do that. I mean, you end up with either having extension methods that convert one to the other, and then you have some sort of conditional weak table that tracks instances or something.
Well, the problem is that if we implement the interfaces on structs, unless we're gonna have these hypothetical devirtualization and optimization features, it's gonna be even
They're
worse.
not hypothetical, they're already implemented. And continuing to be implemented and worked on.
What do you mean? Like now boxing we have boxing into a struct box. Right?
It's disabled, but it is checked into master today. It is disabled by default, but is checked into master. It's the stack-based allocation of heap objects.
And why is it?
Because it's still being worked on.
But let's table this part. So it's
just like tiered compilation.
Even if we assume structs are perfectly handled, right? It still means that even if you do wrapping with structs, you basically end up somebody has to write extension methods and it becomes noisy, right? It's not a great experience because you cannot really add implicit conversions in all cases unless you're willing with taking the dependency. So I think in general, wrapping works to an extent, but I think everybody prefers the solution where whatever your type is, it also is whatever the exchange type is, right? So that you basically are a derivative type of that. That's almost always the better situation.
And most of the tensors are classes. One is thinking about being a struct. Another thing is, do we have actually implementation of methods that would consume these interfaces? Because as we just observed, majority of interesting operations, they kind of need to be implemented natively to be performant.
Right.
Not just give me the raw memory and a rank and an indexer that basically, are these interfaces useful on the consumption side? To have evidence for it?
This is the minimal set of interfaces required, or APIs required to perform other tensor operations except for creating a tensor.
It's like data in out, so like load, transform, feed it in, get the results out, transform back to POCOs.
But
I think Christoph's question, or my question at least, that riffs off of Christoph's is, if could a consumer be implemented in terms of the interfaces that would be fast enough, or would someone actually, to get the perf they need, would they actually have to drop back to the raw implementation?
To get the perf they need, they would need to drop back to the raw implementation, because most of the time you'll end up wanting to do something like GPU acceleration or other types of hardware acceleration to make it actually performant.
But there are two scenarios, there are probably more than two, but contrast the scenarios of actually implementing a tensor DNN library where you want to perform operations versus operating on the edge and wanting to flow data in and get data out and then potentially flow it into another library. And right. So there's that bridge scenario, which is what most of the application authors would be dealing with.
ML.net would really want to use something like this, right? Where one of the DNN, we do talk to both TensorFlow and Onyx today. It's like you could write a transform that just operated over iTensor or iDense tensor, and you didn't know or care whether it came from Onyx or TensorFlow, and you could plug that transform into your pipeline.
So and would that be as efficient as writing one against the core library directly?
I mean, of course, it depends on what you're doing, right?
I would actually say that it would probably, to speak to, I think, Stephen's point is, we would ultimately, if we cared about performance, just work directly against that type anyway. Yeah, the fact that there's some sort of convenience, interface, doesn't seem to save me very much work. Well, because the first thing that I'd have to do if I'm interfacing with TensorFlow is I'd have to figure out how to plug it into TensorFlow anyway by allocating their version of Tensor so that their library can work. Right?
So imagine you had a slice transform where you're like, sure, get the the first 10 elements of each tensor, of each dimension, right? Because you were going to then go do something on top of that later.
Okay, well, I mean, then I have to have an implementation of iTensor to iTensor where I have this slice, and so now I have this other sort of thing which is neither a TensorFlow nor an Onyx tensor, but my own version of it, right?
No, I mean, if you wrote that transform over the slice operator here or the reshape operator, you would get back whatever the native library gave you when you called that method.
You're talking about the slice operation on the interface itself.
Yeah. Yep.
But I mean, that's a very limited view, isn't it? Because I mean, the chance of me wanting to do exactly that, is pretty low, isn't it?
It's not limited at all. Consider you don't actually have to learn TensorFlow's tensor. TensorFlow's tensor would have a constructor that takes one of these, and then we would have a library ecosystem of things, loaders and whatnot, that produce these. And so it provides the common currency to talk between these libraries that all have, at the end of the day, their different preferences for where memory lives and how they can best interact with that memory. But we provide the common currency for those things to work together. Today, if you look at a lot of these libraries, they're forcing people to copy things to generic collections. Some of the worst offenders I've seen pass around lists of lists, and like very, very crazy nested enumerables in order to solve these scenarios. So it's not about, sure, at the end of the day, when you're hitting the metal, that the data is going to be realized in whatever like the Tensor Flow tensor or the Onyx tensor. But when you're plumbing it together, like you won't have to be doing all the data jockeying at like ML.NET won't have to do the data jockeying. You're just plugging the Lego pieces together by calling the constructors that take this abstraction, and then the individual libraries themselves are finding their most efficient way to interact with this abstraction, as opposed to ML.NET.
Okay. So your point is that we're not trying to avoid copies. We're just trying to avoid like the horrible situation where we have jagged lists, and this is an improvement over that state. Is that fair?
So we do expose a span.
Oh, sure, which is great.
That could avoid a copy. In the case that the light up, in the case that the implementation of TensorFlow tensor got something that it realized was a dense tensor and realized it could get at the span and use that memory, then that could avoid a copy in that case. Right. But
and maybe.
Yeah.
Okay.
So I think that the rough overview here is really that some library would take these interchange types as their inputs. They wouldn't worry at the public API surface level about the differences between Onyx tensors or TensorFlow tensors or any other tensor. They would just take the interchange type, whatever it is. Then they would be able to, using these interchange types, say, have specialized fast paths. So if interchange tensor is a torch sharp tensor, then cast it to a concrete torch sharp tensor and call directly into operations exposed by that. And they would be able to do the same thing with an Onyx tensor or any other tensor type. And as a fallback, these interfaces expose enough to be able to view and operate on these tensor types to perform primitive operations if required as a software fallback, if they don't recognize and explicitly support the concrete tensor type.
Okay. One more question. If this strikes me that it would, and I'm sorry I joined late. You doubtless already discussed this point. You are going to be wrapping ISM native handles in some fashion.
What do you mean?
So let's imagine that I have a buffer out of like the TensorFlow library. It's native code, not managed. And I get a float pointer out of it, right? And so then I say, okay, it's a memory of float in managed land. So how do we clean up and handle deallocation?
So
in such a case as that?
So using, under the current proposal, the library that created the tensor would be expected to manage the lifetime and memory of it. There's been some discussion about us also providing a simple implementation over these interfaces as part of the framework, but that's not part of this proposal. But if we were to expose that, we would likely expose some mechanism to allow cleanup and other primitive operations as needed in the future.
Okay.
The thing that I still don't quite get, though, is isn't the purpose of this, as you said, it's mostly for libraries that don't care about the actual types. But I thought one of the value props of this library would be that we model basically what the common shapes of tensors are and give you raw access to the underlying memory. So what could you do better if you would have the actual type in your hands?
You would be able to, so for example, .NET doesn't really have GPU support today, right. But various tensor libraries might have operations that are implemented on the GPU given various size inputs and things like that. Like math.NET, for example, supports a concept of a tensor type, and it supports performing execution on the GPU if you tell it to. So you would be able to go ahead and do whatever is considered best by the native library for an operation if you cast it to concrete type.
So I don't quite know enough about GPU, but isn't the idea that eventually, like, you have basic data that is backed in RAM, and then when you want to run it on the GPU, you basically take the memory, put it on the GPU, do something, and get it back out?
It's backed by some memory somewhere. It could be the GPU, it could be a disk, it could be a RAM disk. It could be some other computer on the network that's holding the actual data for the tensor types. But you have memory somewhere, you perform operations on it, and you get the result back.
You're saying unless I own the allocation of the memory, I may not be able to do the optimizations because I don't know where the memory is?
Right, that could be another case.
Do you always know, is the format of the memory always fixed?
Generally, for a dense tensor, you have a linearized single-dimensional array with some kind of characteristics that say this stride of memory is this particular row or column, like the x index, and then this next section of memory is the y indexes, and then the z indexes, and then...
Well, presumably for the shapes we provide, like the dense tensor, like we make a prescriptive layout, right? Because
that's what the ColumnMajor is. It allows the user to say that the indices are either ordered XYZ or ZYX. Or...
Like, but my point is, given this interface instance, you know what the format is.
Right. So a dense tensor is linear in memory,
right.
And then a sparse tensor, we are non-descriptive about how it is because there's multiple different layouts of how a sparse tensor could be represented.
But then each span of t we return, you know what the order in which things are. Right? Otherwise, you cannot reason about these things, right? So so basically, I guess if there's a new format that would show up, you would enter a new interface, like I fancy tensor of t, and then we would describe what that shape would be, so you can actually interact with that.
Right. So the root tensor has the APIs, which would be the dimensions and the rank, which allow you to determine how big each dimension is, and therefore how to access the underlying memory if you have a dense tensor.
The strides is what you shouldn't be using dimensions, you should be using strides.
I thought we determined we should rename. Okay, yeah, you're right.
No, because if you slice a dense tensor, right, if you slice it and you don't do copying, then your dimensions are changed and your strides actually need to.
Right, I missed that and forgot that we moved strides to dense tensor specifically.
So also, like on the related...
one real case here is the dense stuff, right? Like if I copied in the chat window, WinML has basically this exact same concept, right? They have an iTensor, and then they have tensor int32, tensor double, et cetera, and the way you get at its memory is you call get as vector view, and then that returns an read-only list of whatever the thing is, right? And it's like if I want to write a library that gets at the memory that's underlying the tensor, without an exchange type, you just can't do it, right? You have to write, this is how I do it for Onyx, this is how I do it for Torch Sharp, this is how I do it for WinML, this is how I do it for Tensor Flow. So there are scenarios here, especially around if I can get at the memory and interpret how I should interpret the actual memory using things like dimension strides, is ColumnMajor.
Well,
like now I can do interesting things, right?
Well, you can do interesting things, but if I look at the operations to either read or mutate the tensor, so the indexers, they will be horribly slow in comparison.
For sure. The indexers will definitely be slower than other things.
So which index is the one on iTensor?
But what if you need to get the value? At the end of the day, you need to get the value.
Yeah, so what about the following? We just return the span, the whole memory, and the length of a stride.
You need all the strides.
Yeah, we basically return a span that represents the whole memory.
So
the strides,
that's what we have for
and
dense
then the
tensor.
stride length.
That's what we have for dense tensor.
That's what I.
It's not just one stride length. There's strides for each dimension. Because one dimension might be 10.
Yeah.
Like imagine you have a 10 by 10 grid, right? And now I sliced out 2 columns and 8 rows.
Correct.
Your strides are going to be different for each dimension.
Yeah, and so that's what we have here on iDense tensor.
So and then
right. And then his ColumnMajor too is also important because is it XYZ or is it ZYX?
Right. The thing with you, that's why I said earlier. So assuming I have a dense tensor, I basically can get access to the underlying memory. I can almost spin it and then do whatever I want.
I buy it for the dense tensor with one kind of caveat: the dimensions. Are dimensions always in consecutive memory?
For a dense tensor, yes. That's what a dense tensor is.
Basically, can you
What do you mean by our dimensions always in?
The property called dimensions on iTensor?
Yep.
Can I efficiently just return read-only span?
Oh, I see.
Are
These
you-
are small. These are small arrays. This is the number. You're saying someone might have a representation for their dimensions such that they like interleave the actual counts.
Yeah, exactly.
In various like a heap structure or
It's just like I made the same comment. I made the same comment about non-zero values and get non-zero indexes.
Yeah.
Those might not be contiguous, and so having that be a span might actually be worse because somebody would have to copy them into a contiguous memory.
So you see, if we wanted to design, so let's skip the sparse tensor for a moment. If we wanted to design a dense tensor that is actually efficient for arbitrary memory, I would say I would remove the indexers. I would change dimensions from a span to basically get dimension, you pass an int, and dimensions length gives you that number of, the range of ints that you can pass.
Yeah.
So then you can basically have the dimensions not being consecutive block of memory and still make it very efficient.
Would you do the same thing for strides then? I'd take it.
Let me
get stride into dimension.
Well, is strides?
It's the entire roll.
It's
right?
it's essentially the same thing as dimensions, except it's computed. It's pre-computed. You can typically compute the strides from dimensions. Except in the case
not all the time.
When
Again,
sliced,
slicing,
yeah. In slicing, then it could be totally custom.
So you're basically just suggesting expose this as is, but take the things that are returning a read-only span and change it to return an IEnumerable.
Well, or something like the method. Even the value gives you back the other way.
Yeah, exactly. Just flatten basically the span methods, the two that matter.
Which is the other one you're saying?
Length and indexer.
The indexer. Which indexer are you specifically?
For both dimensions and strides.
Just dimensions and strides, not the actual this indexer.
I would remove the
You said delete it.
How do you get values out of this?
You get to you call that buffer. Have a span.
I see.
And you basically
You
index
force
into a
people
span
to get to the raw, but
that's
they can't do
the only way
that for
to do it
sparse
efficiently.
tensor.
I mean, that's
They can't do it for sparse tensor, and the most efficient way for
Correct.
sparse tensor is the index, or maybe it's some sort of enumerable.
I think sparse tensor. I don't know what to do here. It's never gonna.
Do we have a concrete scenario for sparse
will be.
tensor?
Yeah.
Does libtorch have a sparse tensor, or TensorFlow, or
TensorFlow
Onyx?
does.
But basically, for sparse tensors, you need to know the representation of memory to make it efficient.
Except the concrete types that are implementing these interfaces do know the backing, and so they are able to do it efficiently.
But what do they do when they actually work on it? Do they first convert it to a dense tensor and do work and then go back? Or do they actually work on this thing?
No, they implement the interface, and then the method that is called, get strides or get non-zero values will have all the context of this is how I'm internally represented, and so this is the most efficient way to return that information.
No, I get that.
to the
I'm
user.
saying, let's say you do a computation on a tensor. Is the best way to actually work with the sparse representation over the get non-zero values and get non-zero indices, or do most people end up converting it to a dense tensor, do whatever they do, and then go back to
you
sparse
don't
tensor?
convert sparse tensors to dense tensors to do the operations. You keep it as a sparse tensor. That's why it's a sparse tensor.
Yeah, but I can understand how
It's often infeasible to do it, right? You have billions of virtual values of maybe a dozen real ones.
But I would imagine that the library would basically just downcast to the concrete tensor and get the buffer. It would not bother with the get me non-zero values, get me indices.
These are provided so that users who want to support any tensor type can provide a software fallback.
Yeah. And I do worry a bit about the fallback being so slow that it will be ridiculous.
Well,
Well, that's why it's a fallback. Half the algorithms in CoreFX have a software fallback that are ridiculously slow as soon as you disable hardware intrinsics or vector of t.
So imagine a case where we're still talking about sparse tensor, right? And its legitimacy is that.
Well, or rather, how to design the interface such that it's
It's not.
So I could see a way to use the current one in a valuable way today. So you have some library that outputs a dense tensor and is able, that outputs a sparse tensor and is able to represent it. This is sufficient for representing all of its values, which is a small amount. And then back to the previous example where I said you have some constructor for Tensor Flow tensor that inspects the thing that you give it to see if it's a dense tensor and then efficiently copies its memory. Or it can see if it's a sparse tensor and then efficiently constructs its sparse tensor behind the scenes. So it does its job, but it's only doing its job in the sense that it's exposing enough information to provide an efficient transport, but it's not exceptionally usable. Like, you wouldn't want to write the code that actually goes and interacts with that interface from an application, but an application could pass an object around between two libraries, and then those two libraries could have relatively efficiently maintain the sparseness of the data.
If they understand the concrete subtypes.
No, they don't even need to understand the other concrete subtype. So imagine torch tensor outputs a sparse tensor that's represented in like a dictionary of indices and values. And then Tensor Flow tensor represents a sparse tensor as a series of tensors, where one is indices and others. So it could get the sparse tensor out of torch tensor, and then it could call the get non-zero values and get non-zero indices, and then it can construct its own concrete value. So that the TensorFlow tensor TensorFlow sharp could construct its own sparse tensor, knowing only about iSparse tensor and its concrete implementation. So in that sense, it is satisfying the goal of minimal exchange without having to know about torch tensor's concrete implementation. But yeah, it's not pretty. I've thought about this problem a lot. I can't come up with a great sparseness of
it makes sense, for example, to move the indices from tensor to sparse tensor, because basically, then the usage would be, if you want to take any tensor, you take iTensor. Inside, you first try to cast to dense. Well, you first try to cast to some concrete tensors, and then to dense, and then if it fails, you cast it to very slow implementation that has the indexers. Or you can take dense tensor, then you don't have indices, and then you know that you're supposed to just read the memory and interpret it.
I don't think that's really a good idea. We shouldn't move the indexer to iSparse tensor just because it could potentially be slow for lookup on an iDense tensor. It's still a primitive operation being able to get a value out of a tensor, and you should be able to do that.
Why would you not? Why would it be slow to get the buffer and then?
I mean, what if you're wanting to just in the debugger say, give me the value of?
Then we should add a debugger viewer, if it's for debugger.
No. In the watch window,
or
you
even
want to say local
know.
dot index of 0, 1, 2, 3, and you want to get the value of that index. You can't.
Or just the first. There's cases where you're just like, I know this is a tensor, but there's only going to be one value in it, and so I'm just going to say 0, 0, 0 for the index. Give me the one value out of the thing.
The output of these things could be very small, either single cell or a small table, or it doesn't necessarily. It's not always a bad thing, and I think to me the indexers are primarily useful for fetching the output. Right, that's when people will fall back to the indexers on iTensor, is when they get the output of their DNN and they want to find out how it scored the stuff, and they need something that's easy to use in that case. So we don't want them going down to span. in that case. We don't want them having to do any casting. We want them to have something that's as accessible as a list, because if it's not, they're going to do really bad stuff. They're going to like say, okay, what concrete collection do I know of that I can pass this weird thing to that gives me normal access? And then I'm going to do that, and then that's going to result in a copy. It's like they'll wrap it in a memory stream, then put it in something else, and then like they'll do whatever weird transformation they can figure out in order to get something that's directly usable and doesn't have sharp edges.
I have another question about the sparse tensor. Say, for example, get non-zero indices. How does that work in more than one dimension?
So this was brought up as an open question. And it was believed we probably want something that returns the multidimensional index rather than the linearized index.
Int isn't a valid linearized index, anyways. We should be dealing in longs.
I was about to point that out. Is that int is insufficient?
Actually, we have that problem throughout.
Especially for sparse.
Yeah,
for sparse, int is insufficient.
That's also a general problem with span, in that if you return a span or a memory of t, technically it only supports int.max value.
I know, but in that case, if something's dense, it's often small enough that int is a valid index, whereas that's very often not the case for sparse values, just practically speaking, right?
Right. You could have, several billion, actually, I guess 10 billions of, virtual values, so to speak, and only several non-zero ones.
Especially if you're in the business of having these you have a linearized single index as your return type, which seems to be the approach here.
Yeah, because if you have a cube of, even a relatively small dimension, right, then the linear would be huge.
I mean, you could make the same point about what's it? It's not stride. What was the other word that we had instead of stride?
Slice?
Not slice. Maybe it is stride. Eric was making this point about there being two separate concepts. But I
dimensions versus stride is what I was talking about.
Yeah, dimensions versus stride as being very different things. Strides can often be longs.
So going back to the question of returning span for things like get non-zero values, what Tensor Flow does is they just return a tensor that contains the non-zero values or the indices or the dimensions, since a tensor is just a multidimensional array, and you could have a one-dimensional tensor. So maybe we could just return iTensor of long here.
I checked with Torch, and it's exactly the same thing.
Mm-hmm. Seems reasonable then. Kind of makes sense then.
Yeah.
Do we have a solid use case for iSparse tensor? Did we decide on is it valuable to do right now?
I think we said that there were people that were looking to support sparse tensor, and compressed sparse tensor we threw out because no one was planning on using it right now.
That was CNTK that wanted it originally.
Don't they have a jagged tensor now in the new version? Basically, I mean, the one case I can think of, I guess, is when you try to represent, words in some kind of, one-hot encoding, and then the length is varied. That's a jagged one.
Who's they? TensorFlow?
TensorFlow, Google. Mm-hmm. That's a new thing, I believe, in 2.0 alpha.
By the way, how does Tensor solve the problem of span being only to int max value?
Most of these are native libraries, and they just return long.
Yeah, I know. How does the iTensor solve the problem?
Well, that's what we were just saying, is that we should probably not return span. We should return iTensor.
Yeah, but how does it solve the problem?
What do you mean?
Is iTensor, if it's one-dimensional, can it support more than int max value values?
If it's backed by native memory, it can.
But through
Right, if it's backed by native memory, then you can have your indexer go and index a 64-bit long. We'd have to change this to be long. Rather than
so you would change iTensor to operate over longs.
Right, or maybe we could see what the current plans for inint are, and conceptually make it use that instead. But you either have to do int or long here if you want to support more than int.max value.
So
This is another really good reason to keep the indexers on iTensor. Because if you're returning iTensor from these things, like how are you going to get at the values?
Tensors all the way down?
Well, yeah, then you have to cast it down to iTensor.
Well, but then everything, basically all ints in iTensor would change to longs, correct?
Right.
Could I ask a question about this zero thing? What do we mean by non-zero?
In this case, it's meant to be any value which is included in the sparse tensor. Zero is probably a bad word because you could have -1, for example, be the invalid value.
Okay.
Or you could have zeros in the real values.
Right.
Or you could have like it be something of a read-only memory of car, right?
Yeah.
Okay. All right. I was just wondering. All right. So the problematic nature of zero is known. Okay.
Yeah,
that's all I was bringing up.
Right, because then you'll need to know when you in the method to sparse which ones to exclude, right?
Yeah.
If it's not just
that's a
default.
problem. Yeah.
Oh, to sparse tensor on idents tensor is
Yeah, that's a
Yeah, you have to
big,
know which ones to
that's a
exclude.
problematic. That's going to be a problem.
Right, and that was raised on whether we should have these at all or if they should be extension methods. And we were leaning probably towards making them extension methods because it's not always applicable to convert from one to the other.
Right.
or even as just constructors on the concrete sparse implementations. I could see that, because even an extension method, how do you choose which implementation of sparse tensor that you want to use?
Yeah.
So
Yeah.
we had I was playing with some of this stuff in the prototype because it was convenient to be able to convert. But then when you take away the aspect that we have one canonical like implementation of these things, then the value of that conversion really goes away.
Right.
One of the other open questions was whether we should be exposing a concept of read-only tensor at the base. That way you can differentiate between a readable and writable tensor.
Well, that would be another one of my concerns, is that I see spans, no read-only spans, whereas like get non-zero indices will presumably have to be ordered, I would assume. Is that fair?
Right.
Right. So it seems like this interface is exposing too much of the guts. So yeah, I would prefer the default to be read-only spans, and then we'd have something descending from it possibly be mutable.
Yeah, because often you might have immutable, and then there's no way to express it here, right? If the values are in some native format that you cannot change, right?
Or you don't want to change.
Exactly.
Yeah.
Yeah, like for example, in vbuffer, right? It's basically read-only by default, and you have this vbuffer editor if you want to modify it.
Yeah, and then you have like some sort of path if you really want to, but by default it presents itself as being, yeah. So for example, we could not take vbuffer and have it implement this interface.
Right.
We just couldn't do it.
And by the way, if this is an interrupt type, I mean, that maybe make it even more valid then, right?
What do you mean?
No, well, I'm just saying if the iTensor is something that you use when you pass values between different frameworks.
Oh, yeah. That should definitely be read only, I would assume.
Yeah. Mm-hmm. I mean, in that scenario, right, you're not usually expected to directly, modify them.
Yeah.
We made this mistake with list, and we shouldn't.
Yeah.
But honestly, like if we want to make Sparse Dancer even reasonable in performance, we should do the same trick that we discussed with dimensions. Because the non-zero indices will not be consecutive in memory.
Right.
Yeah.
We've gone over that bit already.
Okay.
So it's not even read-only span. It's basically there's gonna be a flattened span, indexer in length.
There was an open question on whether we should call dimensions shape instead, and whether or not, if we were to call it shape, if we should have a iShape interface or type. That way users can carry additional shape metadata if needed or desired. Some libraries, for example, carry name information along with a given dimension.
And by the way, those are not dimensions, those are dimension lengths, correct? That's what they are?
Yes.
What would dimensions mean if not dimensions length?
The data for it.
I see. The offset of the first element and that. I don't know.
Well, if you go for method, it would be following array, right? Which is get length, and then the argument you pass is the int dimension.
Get length, yeah. So part of this was that the methods on array are not very usable as they are today. Like to get the like primitive type of information like that you might want about the shape, you have to feed a lot of stuff in, call methods multiple times, whereas it's rather convenient to have direct access to the dimensions as a single object. So like there's the debugging scenario, right? And there's also like the workbook type scenario where you're trying to just throw together sample code that uses this and interact with it. So that was part of initially why I looked at array when I created some of the tensor abstractions and created that the single property that represents it as opposed to the get method. But we could always, if we don't like having it expose the read-only span, if we don't like the name, we could come up with a different type that just wraps the dimensions and then provides some efficient access. And people would have to implement that too if they didn't want to, say, copy their dimensions into an array.
Yeah, anyway, after discussing it for now, hour and 15 minutes, my kind of overall feedback would be the following. I would try to use abstract classes instead of interfaces. We don't have a very strong evidence that it doesn't work, it seems. One library tries to move to structs, but I kind of cannot understand how struct here would even like mirror the fact that, you know, it's a bit more lighter weight. I mean, the data is, you know, potentially very large. Struct will be box unless the feature is enabled. The feature probably won't work in a lot of cases. So, like, if we had it as abstract classes, the abstractions would be easier to evolve in the future. And second piece of feedback is, I would implement it, the abstractions and make sure that we can actually get performance that is readable. Because I can totally understand how, you know, downcast to concrete library types would work. And then there's the fallback path. And I think it's fine that it's slower, but I don't think it can be ridiculously slower, or we basically run into the same case that we had with vectors, which is, you know, they either are fast or it's so ridiculously slow that people kind of have to work around the problem.
Well, that's basically what a tensor is. It's similar to a vector in that you're going to end up either doing the accelerated thing where you've got the hardware dedicated to do it, or you're going to end up being really fucking slow.
Well, but I think the problem with vector of t was that if you write naive code, you're still faster than using vector of t in the software.
Well, right. That's because the the CPU is able to actually order memory accesses and things better when you're doing it linearized.
Right. It's gonna be slow, but right. As we just discussed, there's a way to shape the interfaces such that it's faster. For example, if dimensions are not in consecutive memory locations, then it would be better to have the get dimension length and dimension length, and then maybe solve the debugging problem. The high level point is, I kind of feel very uncomfortable with introducing new abstractions to BCL without having kind of vetted implementation. And I don't know how much we've done that.
So the using classes still ignores the biggest win of interfaces, which is being able to carry the original concrete type along with the interface, along with the abstraction. As soon as you have a wrapper type, you lose the original type information.
No wrappers.
Then you already have a case where people can't always implement the interchange type.
Why?
As soon as you have a struct, or you have or you yourself are exposing tensor and dense tensor, you can no longer inherit from R types because you don't have multiple inheritance.
You can put at least tensor at the very top of the hierarchy, right?
Potentially, you can put tensor.
Yes. And then
have
basically,
that inherit.
the reusable library would downcast to your type, and if not, it falls back to tensor.
Yes, but then you lose half the value of having dense tensor and sparse tensor.
You already are in a fallback class.
Can we make tensor a base class and then dense tensor an interface? Like, is that stupid?
Well, then you would still need an interface to define tensor that iDense tensor would inherit from. So then you have both interfaces and classes.
Mm-hmm.
I actually, the suggestion that Eric had, I like it much better than just interfaces. And the reason for it is we would have the top type, iTensor, not iTensor, but tensor of T. The libraries would take it, and then every other type is just a downcast for potential performance optimization. So if we ever need to evolve the interface and we have now I faster or I better dense tensor, it's just a interface. It's a peer and then downcast, try to cast to it too.
But then you still have the problem of most people would want to implement, and some people would have to implement the interface, and you wouldn't be able to evolve the interface. You're just duplicating work.
What? Which interface? The dense tensor or the...
Well, if you have iDense tensor, you also need iTensor. That way you have the same abstraction.
No, you inherit from tensor of T. At the top of the...
You can't have an interface inherit from iTensor of T, or from tensor
and
of T.
interface would not implement. They inherit from... So the hierarchy would be the following. Or then bunch of types. My tensor, my other tensor, blah blah blah, up to whatever the concrete type is. And then this would also implement interfaces iDense tensor.
Yes, but iDense tensor still needs the root tensor interface because you're going that way.
Why? All I want off of it is the buffer and the strides and ColumnMajor. That's all I really want. I want to see, are you a dense one? Oh, you are? Let me get you directly to the buffer.
Exactly.
Because the advantage you get there is you could have an iDense tensor and an iReadOnly dense tensor, right? And if you just wanted to read them, cast it to iReadOnly.
You still have the broken problem of if you want to accept a tensor but determine if it's a dense tensor.
You do an is check.
You just...
Then I use the abstract class, tensor of T.
Right, but as soon as you have something which is not a class, you can't have the proper hierarchy.
Yes, why do we need to have something that is not
Because there are people, not just the four partner teams we've looked at, but other libraries out there that are using struct types for their tensor types.
Do we know that?
So we said that, Matteo said that TensorFlow Sharp is moving there. I've also seen folks who want their own type hierarchy for their tensor types because they treat them like handles. And they have base handle types that deal with managing the memory that these things back. And so they want the type hierarchy to represent their handle hierarchy in all their common memory management and ref counting methods. So that was the...
Yeah. So
there's a multiple inheritance.
So then they would have to wrap. But the thing is that I'm absolutely sure these interfaces will not last longer than a few years. the space is so evolving. We're adding ranges, this and that, and like.
I think
I've seen this so many times. We keep adding interfaces. Then after a few years, like they are basically obsolete. We just, like, just my 2 cents.
Then convince the runtime team and the language team to support multiple inheritance, and to support inheriting for value types as well.
We're not going to support ever multiple inheritance classes.
Right. So you have a fundamental problem in that you have types that need to support an interchange type and can't because
they have to run. They would have to.
Right, and then you lose the type information.
That's too bad.
And so users who are looking to squeeze every ounce of performance out of their performance-oriented libraries, we're basically
then
telling.
Let's add to the abstract class at the very top. Let's add object property. Underlying, like we have underlying tensor or original tensor. And it's an object you can downcast to whatever you want.
That still seems like a terrible way to go about it. Basically the only concern here for the interfaces is if you want to extend the interface to support something like operations in the future, you can't do it.
Correct.
Without exposing the interface.
That's one. Yes. Sure. Let's say this is the very main one.
Yeah, and
not just operations, just anything, right?
Right.
It's a one shot. It's the general problem with interfaces. You get one shot at it.
The only interfaces in DCL that kind of survived are super, super simple, that existed, like the concepts existed for years and years and years.
Yes,
like
and
very simple collections. All the others, we have problems with them.
And
they are either not useful, so nobody consumes them, or they are obsoleted after a few years.
And the base concept for a tensor, which is effectively a multidimensional array, is this. This is the base concept that has persisted for years and years.
Just the concept, but I bet we have the APIs wrong.
Yeah,
just like how we discussed, there are so many different ways to.
Just like we got iList wrong, right?
Yeah,
iList is also.
So, but that persists. So we're trying to. So don't look at this as a starting from zero. We're starting from iList, iReadOnly list.
Yeah, and there's other things that
we're trying to build off of that.
There's definitely other things that we've screwed up even recently, like span probably should have supported long length. That way it would just work with native memory without all the span sequence and other extensions we've had to have. But we messed it up.
We didn't mess it up.
And
seriously,
that's your opinion on it. But
yes.
Correct. Myself and many others would say we messed it up and we have to live with it and the consequences of it.
I'm super happy that we didn't make it long.
And libraries like ML.NET and Tensor Flow and others have to work around the fact that span doesn't support long lengths because they're frequently working with memory that might be long lengths.
To be fair, though, like there was a decision that we made that was based on a trade-off, right? But I think the question here is if you to me, it's not so much the fact that can we fuck things up, right? Because the answer to this is always true, right? Yeah. But I think the question is how likely do these things last a few releases, right? And I think one thing we already do now is that when we look at indexes in particular, right, we know that we want to think about how we will support index in range in the future, right? Or, C#9, one thing that Matt's is looking into is numerical types and roles, right? So the question is, with those things in mind, like how long will these abstractions last? Now, using an abstract base type may not be the, silver bullet to make it guaranteed to be evolved, but you have a much higher chance because it's easier to add an overload to an indexer than it is to say, well,
I can imagine
new base
instead of downcasting to 25 different implementations and trying to downcast, we would want to add a property that is non-tensor libraries that returns an enum value that tells you which tensor it is, so you don't have to keep downcasting.
You still have to downcast anyway.
You have to downcast once, not multiple times.
I don't think we've ever been talking about downcasting to dozens and dozens of different types.
Yeah.
Really?
People would generally support one or two libraries, and they would fall back for anything else.
I can't imagine them supporting more than one, to tell you the truth.
Yeah, their own type.
Honestly, I don't fully get the.
Over years, there's going to be more and more.
I don't fully get the try this one, because if you're going to try libtorch, then you have to have the libtorch binaries there to call into it. If you're going to try TensorFlow, you're going to have the TensorFlow binaries there to call into it, right?
Well, it's dependency injection at that point. You're able to provide a single public interface that does the checks in the dispatch to the appropriate
Anyway,
extension.
I just use it as an example. I can imagine a property that basically tells you, hey, yes, there are 3 libraries that we know about, TensorFlow and PyTorch and whatnot, and we have a property that tells you which tensor it is. Just an idea. Like, those are the things that over time we may decide that we want to add, and then on an abstract class, it's possible totally to add, because you add an enum with a value I don't know, and then you add return it by default, and then implementations can override the method and return the enum value that they are. This is just one example. I'm just giving you an example.
And then you end up with people who are creating wrapper types, even for the cases where they have classes, and where they're creating generic they're basically specializing 10 different class types that inherit from our dense tensor, which is exactly what was happening with the previous abstract class mechanism we were trying to expose, because people are trying to work around perf issues and other problems with exposing the abstract class.
What are the perf issues?
You have to have heap allocations. You're losing the type information.
I don't understand how you have to. What do you mean by heap allocations? We just said
you have a
all
class.
tensors are classes.
No.
One is toying with abstract.
Of the 4 we've checked, there's 2 which are currently using classes. There's 1 which is looking to be a struct, and I don't remember what the other one is.
Okay.
And then there's a number of external libraries that aren't
what is the performance
forward-looking.
problem? You said that 2 are using classes. Do they have performance problem?
I'm not sure if they have performance problems.
I think that they don't have, because they haven't tested. So I can give you my use case because I moved to struct. It's basically, as far as I know, TensorFlow Sharp does not provide training. I'm trying to do training over Torch Sharp, and when you start to have like several transformations over the tensor, and you loop them into like thousands of tensor, because that is the data they flow in, you basically generate a lot of objects in the heap, and that kind of crash the performance. Right. So that is my use case, but I don't know if the other system they try with the same use case. But of course, that doesn't mean that we need to have like iTensor in the training path, right? Because in theory, I should only use iTensor when once they train, I want to move my data to some other framework, right? So it's kind of a specific use case, the one that I'm doing right now.
But would structs help you? Because you still have to bake it by memory, right? So if you create 1,000 tensors, your tensor classes are not the problem, right? It's the memory they're holding on to.
But you're not thrashing the GC at that point with a bunch of new heap allocations every time you want to slice or reshape the tensor.
I'm not sure I follow. Like, if the type is mutable, right, and the memory is mutable, then who cares whether you have a small object holding onto the memory?
Because you have to create the object, which gets tracked by the GC. A lot of times, these objects for slicing and stuff are short-lived. It's the same problem we had with span. You end up creating a lot of short-lived GC-tracked objects that are just wrapping memory. That is the perfect use case for value types.
Maybe I'm not entirely sure, but my understanding is that, like, if you create 1,000 tensors, is your problem really the 1,000 instances of the tensor type, or is your problem that you have 1,000 memories that are baking that?
I have 1,000 tensor multiplied by so the 1,000 tensor are the input data, and then on top of that I have to do transform. So out of 1,000 data tensor, I transform them over 20 transformations. So now you have 20,000 tensors that you leave in memory, and one epoch take like a few seconds. But you need to dispose all of them.
Those transforms aren't in managed code, though, right? Those transforms are in the
unmanaged code. But I'm creating object for all the type of transformation that I'm doing. So I'm doing I have like 10 layers, and for each layer I'm doing a tensor transformation. Therefore, I'm creating a new tensor out of that, right?
So no matter what you have, whether you're doing a value type or a class on the C# side, on the native side, you have all the memory that's backing it. The problem then becomes, once you move to the managed side, do you have a zero-cost abstraction over that? Or are you incurring a 34-byte heap allocation to wrap every single one of those tensors you have on the native side, and then more objects created for every single time you want to slice or reshape that tensor? In which case, the underlying view of the memory remains the same. You're just creating new heap allocations to track the different slices of the memory that you're looking into.
Exactly.
And the average GC object, even for just, an empty object, is like 34 bytes. And so you're incurring that 34 byte overhead for every single time you slice. And if they're short-lived, you have the GC thrashing every single time you have to allocate the object, and then and then the GC says, "Oh, I can free it." It's all the problems we've been working with and working around by adding span and everything else.
They could solve the problem by having my tensor slice correct type that is a struct.
Yes, you could potentially have that. And then that itself...
That thing can't inherit from tensor base class.
Right, but that slice is itself a tensor. And so you generally want to operate on that slice as if it was a regular tensor, because it is a tensor. You've got tensors all the way up and down.
When you're in their world, you want to operate.
I mean, when you're working with tensors.
When you work through our abstraction, that's our off. We return I tensor.
Right.
It's going to be...
In which case, if we return an I tensor for dimensions, for example, then that could just be a regular... They could have a simple tensor that represents a one-dimensional array of that backing data and that efficiently accesses everything.
Anyway, we are discussing too much detail. I said what I still think. I think there should be done more validation experimentation that we are doing same things here. It seems like we just created a bunch of abstractions that can be implemented on types. We don't have a very crisp picture how they would be consumed, what it would mean.
I think we do for dense. I think for a dense tensor, I think we have pretty concrete scenarios for how it will be consumed.
Well, you mean you think not that somebody implemented measured perf, validated that the performance problems with classes was because of the classes and not because of fundamentally something being slow in the algorithm and the object allocations.
Most of the times, these are fundamental problems with the algorithms because the algorithms are written in native code and have been perf tested for years.
If the algorithms are written in native code, they won't be doing thousands of slices.
No. The users might be slicing on the managed side before passing it into the native side.
I understand. If they slice once, it's not a big deal. It's going to be an allocation. I wonder whether that's where the bottleneck was that he was talking about. That, something was taking seconds.
The algorithm size is fixed in the sense that I am just implementing a neural network model. I'm NIST, so the algorithm is fixed. And by just changing class to struct, the performance improved by 2x in the wrapper around the native tensor. That is what I observed. I have the test, so I can tell you how to run the test, etc. It's open source, etc.
Yeah, if you could send us a link, I would be very interested.
Yeah, sure, of course.
Yeah, the thing that I don't understand is though, so let's say even you have value types baking that, right? So that you basically bet on the fact that the JIT will eventually be able to make slice returning an I tensor and not allocate, right? Which may or may not be the case, right?
Yeah.
No, I think they were saying that forget about these abstractions.
Okay.
The code today, they had an experiment. Their tensor type, independent from these abstractions, was a class and a struct, and then they just ran some performance test and it was 2x because of a class.
So that one I buy, because basically if you have structs, you return structs, I mean you don't allocate, right? Like you can have your own slice method that gives you back a new struct, right? And then you don't allocate in the slice method modulo the native memory shenanigans that you have to do. But like as soon as you implement I tensor of t, like your slice method has to return an I tensor of t, not...
Yeah, but they don't care about it. They basically say, in majority of the cases, users will work with the concrete type. They don't want these abstractions to suddenly hurt the scenario where somebody's working with concrete types. But you said that you completely can see how it's 2x because they moved, and I would want to still see the test because the tensors would have to be super, super small for the heap allocations to suddenly make the scenario 2x.
You're in a training loop.
If you're in a training loop, you shouldn't be using managed APIs. We all agreed on this, correct? Okay, well then you're not gonna be using the managed slicing.
Wait.
Torch is a little bit different.
I don't think that's true, and I don't agree with it.
Torch is more of an interactive library. So the way that it's less like TensorFlow where you set up this big graph and then just feed a bunch of data in and get data out. Yeah. Torch is a more interactive.
And by interactive,
framework.
What do you mean?
I mean, like you're calling the operators directly as opposed to, it's not the pre-canned graph. Like think back to our MLNets discussions with respect to like pre-canned, like a functional graph and then calling just dot execute versus Mateo, like you guys,
less declarative
and more here, but you guys can probably do a better job at contrasting Torch to other DNN frameworks than I can. But my understanding is that it's more of an interactive experience.
Meaning like you have a chatty coordination between some sort of console app and some sort of managed API service.
Well, in this case, you're basically using managed API surface. Can you get like does perf even matter at that point?
Yeah, imagine a different framework. So we have a chatty native interop layer. We want it to be low overhead, right? We don't want to force people into allocating an object every time the p invoke returns.
No, not every time the invoke returns. Every time that slices code.
So, say the output of the p invoke is a tensor, and the tensor on the native side could be reallocated, could be reused, but the native side pools the memory. But we have no way of even pooling these things.
We are doing native interop of something that behind the scenes changes memory, reallocates, and we worry about a single allocation?
I think it would be, we've got plenty of cases where this matters for our networking APIs, right? And like, you don't want, like you're interacting with a bunch of HTTP headers, and you don't want to be allocating every time you read one of the header values, right? So, I'm trying to just generalize to a more, imagine something where we have a more chatty interaction model.
Well, because today in HTTP client we allocate very complicated collections of strings for a single request, so for what amounts to single p invoke code. Well, that's much bigger problem than a single allocation per p invoke. Anyway, we now drilling into the thing. I said what I said. I think it would be good to illustrate the problem.
I see. Yeah.
And do some implementation, some bake time. Like, have we had these kind of long enough in CoreFX lab to make sure that this is the shape, this is the...
Yeah, I tried to make this actionable. Like, what would maybe help is if we can get to the point where we can say, well, we have abstraction. Would we ship any implementations, or would we only ship abstractions?
Well, so there's a proposal to for if we expose these interfaces to also provide potentially a primitive abstraction, a primitive implementation over these to assist with software fallback cases, or for cases where users just want to play around with the tensor without being dependent on a core library.
Yeah, so I think in general with abstractions, what you really want is you want to make sure you have at least 2 implementations, right? Because otherwise you have no vetting for the interface.
Implementations and consumers.
Right, but I'm saying, ideally we would have, let's say, TensorFlow Sharp implementing those, and then maybe we have a set of implementations that we provide people that we think is good enough for a subset of customers, right? And then we can say, well, does that actually hold up? Do the abstractions actually hold up well enough? Can they model both sides? Can I write code that can work for both sides?
Consumers are more important than implementations. I totally cannot, implementing an interface is usually much easier than consume it in a sane fashion.
I agree, actually. Like, if we have the cases of, say, two neural network frameworks using it, and perhaps, VBuffer or TLC or ML.NET, sorry, and then perhaps, can we write like a mini, pandas library or something to do something with it? Or is that not the goal here?
On ML.NET, we could imagine what's it called, prediction engine accepting iTensor as one of the potential input types, and we try to make it as efficient as possible and see what happens.
See, the way I was thinking about it for MLNet is a tensor type in the data view type.
Okay.
Like we have tensor type today, but
You're saying the VBuffer of that?
It wouldn't be a VBuffer of that. It would just be iTensor or whatever the core type is here. That's the type of that column. No VBuffer.
Okay. Well, let's imagine that we don't do that because, despite what Christoph says, we do actually find struct types kind of useful for our vector types. So I don't know. If
but this isn't a vector type. This is a tensor type.
I know, but I don't really feel the need to shift to a new type because I found
you realize what we're doing today. You realize what we're doing today with Tensor Flow in Onyx, right?
Sure.
We copy the data back and forth.
Oh, sure, but this won't solve that problem, will it?
Of course it will. If we have an iTensor type and TensorFlow returns ML.NET an iTensor type and says, here's the data, and then MLNet doesn't need to copy it into a VBuffer. All it does is like, okay, here's the iTensor type. Let me keep it in the pipeline and go with it. No copies need to happen. It of course solves that problem.
Right, but then every component.
I don't think that as soon as you introduce more components that does more operations on top of this, you will have to copy it again. I mean, it defers the problem. It doesn't solve the problem.
Yeah, maybe.
But okay, but if we do this, if we have a data view that has that column, then like we have to have operations on those, right? Like every transform is designed to operate on a certain kinds, and it doesn't know anything about tensor. How hard would that be to rewrite them, basically, or at least augment them to to support that type as well?
At some point, you have to do the copy again. That's why I say it it only defers the problem. It doesn't solve it, and it defers it in a fairly ugly way, I'd say. So that's why I would prefer to just.
This is exactly what I was like. This is an awesome scenario. Could ML.NET consume one of those that is returned actually from TensorFlow and make the scenario even valuable?
Well, that is a good
test, It does today.
Let's check it.
It does today, and we copy the data out into a managed array.
We'd have to continue copying it out because, what are we going to do? Have concrete type sets say, okay, if you're a TensorFlow vector, now you have to have this other code path.
That's what we just talked about for 45 minutes. We were just talking about.
I know, and I would say that for MLNet that does not work because, if I have a specific transform, how does it even know that TensorFlow exists unless we have all of our transforms depend on the TensorFlow thing, which we don't want? That's
exactly what I was saying 15 minutes ago, is that common libraries aren't going to know about each one of those.
Right, in which case MLNet will not use iTensor as its internal type. It might speak iTensor, but it won't use iTensor.
Well, and then we'll throw when the downcast fails, correct?
Well, I would hope that we have a backup plan, not
basically,
throw.
I would imagine ML.NET would do downcast to its own tensor vector, for example, of T. If it fails, it would somehow attempt to copy, if it even knows how to copy the data, into vector of T. And then otherwise, if it doesn't know, it would just fail. It would not use these APIs on these types.
Right. The entire principle behind these APIs is you take them at the public surface area point, and then you do the type check for if this is well-known type, cast it to that. Otherwise, you could either throw or provide a software fallback saying, I'm going to try dependency
I was saying
injection.
What they will do, not what you can do. They will not have a software fallback. That's what they were just saying.
Right. In which case, they would have to throw if they got an iTensor that was an unsupported type.
Which, honestly, I would argue...
We would probably copy it to our own internal types. If we saw an iTensor and we didn't recognize it, we'd say, okay.
Well, then maybe
we'll just copy out.
Maybe the interface should just be, copy to... I don't know.
I mean,
Yeah,
that's what,
copied of what?
that's what you get with dense tensor, right? You get the buffer and the shape and the strides.
That's the purpose of the exchange type, is it provides enough that you can build up and do any other operation with it, but it only provides the minimum to do the other operations. If you wanted to do copy 2, you could do it using this.
I hope we all see in the room. It would be awesome to just implement this scenario and see what ML.NET would do.
Yeah.
And then we will know what APIs we actually need and what
A very simple scenario.
There are 3 implementations of the scenario today. It's just there's not the converged. There's not the MLNet layer. So
Well, it is today. The Onyx runtime exposes tensor of T, what we have in v.1 today.
Mm-hmm.
That's what Onyx runtime gives back to its managed consumers. ML.NET is one of those managed consumers.
Mm-hmm.
And it uses tensor of T. ML.NET is dependent on tensor of T today because it depends on Onyx runtime.
Right.
We have this scenario today.
Mm-hmm. Nice.
Well, how does the interop work if you don't know your producers, and producers and consumers don't know about each other, right? Which is basically the value of the abstraction, is to say there's an exchange type that both sides that don't know about each other can agree on. Like, in those scenarios, are all basically going down the path of saying either I know about the actual tensor type, or if I don't, I copy it to my representation and move on. At which point the value of the abstraction is literally just be an interface and have a single method that says get it into the shape that I know.
But at least that is value, right? At least give me the value.
Simpler API server that would just converge to a single, almost like a single. Basically, it would basically make the part of the iDense tensor the exchange type, which is basically the, give me a dense tensor representation for copying purposes.
Yeah, but that's not always valid. If you have a sparse tensor, then it's not valid to necessarily get the entire.
Can ML.NET today consume sparse tensor?
No, because it doesn't exist.
I thought
Would it
tensor of T
consume
had
if we had it?
If we had iSparse tensor, then there's libraries that expose their own concept of
Would
sparse tensor.
ML.NET consume?
I'm not sure about ML, but ML has its own concept of sparseness.
That's the point of the exercise. So we keep saying that we have some code.
It could convert a sparse
how
tensor
it
to be
would
buffer.
all work together. Because maybe the only useful abstraction is dense tensor, and sparse tensors you cannot interchange them. I don't know what the answer is. It would be good to implement it end to end and not.
Well, we can't exactly implement end to end until after we have an API surface, which can be checked into CoreFX and then given out as an experimental package.
Why does it need to be in CoreFX?
Because we're looking at shipping it because people are needing this interchange type.
Shipping a stable or not?
Where we need, after we get an approved, so the original plan was after this gets reviewed and potentially approved, we would check it in, we would ship an experimental package to allow people to consume it, and then provided we don't get more feedback saying this is absolutely terrible, then we would finish stabilizing it and then ship it before 3.0.
If it's not stable, if it's not like, it's added to BCL and then it ships and then it's moved into the core.
It's not supposed to be part of BCL. It's going to be out of band and always out of band.
Yeah, I think if the purpose is to ship a preview to the validation, I think I'm fine with that. The question is just who's on the hook to do the validation. Right? We shouldn't just ship an unstable package, blog about it, and then say if we don't hear negative feedback, we ship stable, because
it's
measure of
on
success.
my plate to push this through, make sure that everyone's okay with the shape, and Christoph's had a lot of negative feedback about the shape. And then go and continue working with the teams that I've already been working with, and Eric Earhart has been doing some as well, to make sure that they are picking it up and implementing it and getting the feedback. We've been iterating on this for well over a couple months now.
Yeah, what would be, as I said before, like I can see the general principle is that we basically provide access to underlying memory structure so that you can effectively extract the data in an efficient way as possible, right? And there's two ways we know about it: dense and sparse, right? But it would be useful, like once you did the experimentation, to see what happens at the edges of these systems, right? If they effectively all end up just getting the memory, copy it over, then I think the abstraction could be much simpler, right? In which case, most of the concerns about them being interfaces might disappear because they become super simplistic, right?
Right, but
like
then
right now they become like more of a a useful thing that you expect people to actually consume an API service, and that kind of opens up the thing for saying, hopefully we want to evolve the mechanics, right, the way the indexer works, right? Or let's say we add a new iFancy tensor. Now you basically want the method to fancy tensor on both dense tensor and sparse tensor, and you're now screwed because you cannot add a new virtual method on that one, right? So that's why I think if we go down that path, I think we really need to validate that first the methods are actually useful that we have, and then we know how to evolve it, right? So let's say we had a third one or a fourth one, how would that even work? Because right now you would basically have to version the existing interfaces to add a third one to it.
Well, I think based on the meeting so far, we've said we would remove the 2 sparse and 2 dense tensor because they're not always valid.
Right.
We would expose the read-only concept, and then you don't. And then if you want to expose a new thing that's not dense or sparse, which I'm not sure I could conceptualize that right now, because you either have something that has all values or doesn't have all values, then
There's ragged.
Then you expose it.
Or jagged, sorry.
Right, but isn't that just a dense tensor where the memory's not linearized?
And then strides become
could be sparse.
available, right? In that case, strides don't make sense anymore.
Yep.
I mean, let's imagine just the most basic thing. I mean, you have like a batch of text, and then you tokenize it. I mean, then you have one sentence with 7 words, another with 10, another with, 5. How do I represent that? I mean, that's one of the most basic things you can do in text processing, and I'm not sure how I'd represent it here.
And each one could be a sparse thing, by the way, as well, right? Because you can have like some word embedding or whatever.
Right, maybe.
Right.
Like each word could be represented sparsely.
Yeah, that's fair.
I mean, that's what actually, I've sent a link. I don't know if you've seen it. It's a ragged tensor. It's a new thing. I'm just saying, like, there could be other concepts coming in the future, right?
But that
it's not a closed set.
That would also be neither dense nor sparse, and so you'd have another interface which inherits from iTensor, which is a separate core concept. And if you don't have the conversion methods between them, then you've got no versioning on the previous interfaces.
In that case, I'm not sure that I would actually use iTensor at that point, would I? How could I?
How could you not?
Well, I mean, I just say I have like a jagged thing with like, say 3 sentences, lengths, 12, 7, and 13. What is dimensions? I don't know. Rank is 2. I get that. Then I have indices. How do I tell that there are only 12 in the first, instance, 7 in the second, 13 in the third?
I mean, you can already have that with the tensor today. You can have something that has different lengths for each dimension, and that's what dimensions exposes.
Okay, but I'm not saying different lengths for each dimension. I'm saying different lengths for each, sub sort of sentence, right? Because I have sentence 1, 2, and 3.
Right, but that's
the first has.
That's basically a tensor of tensors.
Is that really something that we want to have? Tensors of tensors? How do I have a read-only? How do I have a span of iTensor of T? Is that even possible?
I don't see why you wouldn't be able to have that.
All right.
I mean, once you move to tensors, everything's a tensor. An array is just a one-dimensional tensor. A scalar value is a zero-dimensional tensor. A vector is a two-dimensional tensor. Everything's tensors, and so everything can be represented as tensors. If you have something which is, where one thing is 7 characters and one is 3 characters and stuff, you could just represent that as a tensor of character tensors.
All right.
And I would imagine that's how, like, Tensor Flow, given their existing surface area, which is basically what this is, minus some differences in what they call things, it would expose it.
Okay, is that actually how they expose it, Mateo? Do you know? Or anyone?
I'm looking at TF Tensor right now, and it just exposes it exposes shape, which contains dimensions and rank.
Okay. just be sort of interested in how like a text processing library would do something as basic as tokenize. But maybe we can talk about that later.
Also, another question, is there like a way to have samples with that, API shapes, like here, how we go from ML.NET to TensorFlow, for example, Tensor or whatever. If we have that exercise, that might be quite enlightening. Like we were talking about, not necessarily shipping it, but just like as a part of design process, can we make some, mock scenarios, I guess, and just so it's more visible.
It's almost like the guidance that you would give people, right? Like if you were to implement something like ML.NET, how should you consume tensors? And then if you have something like TensorFlow, how should you expose your tensors, right?
Or yeah, exactly. So like imagine you start with, let's say, TensorFlow, then go to Onyx, then go to ML.NET, or in some random order for that. And how does that actually going to look like? I mean, is there usefulness in this concept between them, or are we just going to go between the native types anyway? Or perhaps the other thing is like, if we have this type, will there ever be like a math library that's based on it, right? Can we do like math operations on tensors? Like, would those math operations be efficient given the current API structure? Or they have to go through some, I don't know, some hacks
they
to do
could certainly be efficient for dense tensor since you have access to the underlying memory.
Right, but I'm just saying, like, what kind of operations, right? Like, I don't know, matrix multiplies or whatever. What other things you could do with them efficiently? Is a current API good for that?
I mean, there can definitely be more investigation here, but what we're basically discussing, even if just like prototyping some of this is a very significant investment for prototyping things, and right.
But I think that I mean, like in a sense, that's kind of like somebody has to do that homework, right? Because,
right,
like fundamentally, like if you ship an exchange type, you need to be able to say what's the expectation for a producer and a consumer, right? Because the whole thing is scenario driven, right? So like once we know what the requirements are, then we can judge the APIs. But otherwise, it's hard to say who's using, for example, the params-based indexer. Like, is there anybody ever using that? Because if the guidance has never used it, well, then maybe we shouldn't have the API, right? Or maybe we say, well, you should never use it. However, the API is used in debugging, right? Or whatever the case might be, right?
And the sparse tensor, even I have much bigger. I can imagine the dense tensor. We could have an abstraction that actually is useful.
I mean,
I have much stronger concerns about the sparse tensor. And the moment we say it's only dense tensor that is useful, then maybe we only need one abstraction, dense tensor. And if you in some other case, you fall back to throwing an exception, just like ML.NET would.
But you often don't have a dense tensor because a lot of times this data is
and
huge.
ML.NET will not, the moment they detect that it's not dense tensor, they will throw an exception. So if none of the consumers will ever use the sparse tensor, they will always, I'm now in the sparse tensor case, I throw, then it doesn't make sense to have this abstraction.
There will be sparse tensors. I think it's less clear how that can be generically represented, but I do think that we have multiple frameworks that deal in sparse tensors.
Correct. That will anybody consume a sparse tensor.
Stitching those.
I mean, if the data is sparse, there's often no other way to do it due to just, computational cost, or memory cost, right?
Right. I mean, where did we get the idea that if we got a sparse tensor, we would throw? Is that something that I heard mentioned? Where did we get that idea?
Well, I think you said that. You basically said ML.NET would take the abstraction to the constructor, would check whether it's one of its tensors, then maybe try to copy the memory, and then basically would fail.
No, I said if...
No,
I said it would fall back to dealing with this abstraction. And if the constructor could handle a sparse tensor, it would deal with the sparse abstraction.
That's not...
I think what was said is that basically, each individual component knows how to deal with the buffer, and so that they believe it's kind of like tightly coupled to it. If it sees a tensor, it's like, I don't know how to do with this type, it skips it. But what probably a more reasonable thing to do is to convert to a VBuffer from this tensor, and then we don't have to modify the entire library to know that other type.
Yeah.
That's all we're saying. But the vBuffer, interestingly, supports both sparse and dense in the same exact instance, right? And it's kind of
we tried to sort of like pull that apart. I think Eric tried to pull that apart, and it wound up being more confusing than helpful. So we backed off that.
Right, but the interesting. Sorry, go ahead.
But I think that so if we were to do this conversion into and out of vBuffer, we would ultimately be implementing sort of wrapper types that implemented one or the other without having vBuffer implement iTensor itself, because I don't think it could.
Right. Mm-hmm. But the interesting example is if vBuffer is both dense and sparse.
I know that's why I couldn't implement one or the other, because it could be either.
But you could implement a vBuffer that is backed by a tensor, right?
No, because vBuffer is not. vBuffer relies on having a very specific memory layout.
Yeah.
Okay.
Right. vBuffer is type. So
right, it's
what about
a real thing.
It's a concrete struct.
Okay.
vBuffer is a concrete struct.
One thing that I can help with, since we have already the previous version, the abstract class version of iTensor in Torch Sharp, and now I'm trying to integrate the Torch Sharp with Meltonet. I can try to look into that while I'm doing this integration, if it could help. Like this, I mean, how to use the iTensor to move stuff between the Meltonet and Torch Sharp, and vice versa.
Is that helpful?
Yeah.
So what would we need in order for is that Matteo who's suggesting?
Yes.
Yeah.
Yes.
What would he need from us in order to make that work? Does he need us to commit this API in CoreFX?
I think we need to have this API in some consumable package to be able to have the external libraries be able to use it in any shape.
We could add this API into the current package and have it be side by side, right?
Yes.
Yeah. So it's not. I mean, we don't have to break existing consumers. We can add this for experimental purposes, even though it's in CoreFX right now. And that could enable us to.
What do you mean by side by side?
There's already the concrete types, so we don't need to go and delete those and potentially break people who are pulling tip from CoreFX in order to try out this new strategy.
So that side, you basically would just add new types to the existing URL.
Yeah, but then we still would need to coalesce, but we could do the experiments we're talking about.
Right. Yeah, and before shipping, we would remove one of the two implementations.
I mean, in general, it seems to me like it should not be that we need to ship to NuGet.org to do an experiment, right? Like we should be able to do the experiment purely from committing to master, building a myget package, getting the package out, somebody reference the feed, right? That should unblock at least the people we are partnering with. I understand that you will not make inroads for some third party team that may have some interest, because that's a pretty high bar. But I think for us, we should be able to make progress on, okay, is this shape sufficient? Like, to me, it's really about, like, can we define what a consumer would do and what a producer would do? And do we have confidence that if they don't know each other, they have a sensible, ABI to talk, right? And that's really what it is, in my opinion. Like, I mean, as long as we have that, then we can argue, okay, do we have enough consumers? Like, do we think one is enough? Do we need another one? But otherwise, it's a bit like reading tea leaves, right? You're saying, well, I think this is what a tensor looks like. Okay, but is this true for like the next 3 versions, or is this true today and will not hold in 2 months from now?
So this is currently true. The rough shape here, ignoring some of the type specificness, is the rough shape that all current libraries I've looked at agree that a tensor is.
Right.
And any of the libraries, if they wanted to change what this core concept of a tensor is, would have to themselves be making a massive breaking change to their library to support something different from this. This is basically the absolute minimum of what everyone agrees a tensor is.
Well, I think I said it earlier, but I think that to me there's two sides to it, right? There's the concept and there is the mechanics, right? And like if you design a type to be directly consumable, like with indexes, you also have mechanics on that type, right? And those do change all the time. Like no matter whether your concept changes, right?
Well,
Stream hasn't changed concept; it has changed mechanics.
I think there's implementation details of how something changes, but the base principle is that a tensor is effectively a multidimensional array, and therefore you are able to index into it. And if it is row major order, then the indexes are interpreted this way. If it's column major, they're interpreted this way.
Sure. Like all I'm saying is that stream is in the same bucket. Stream hasn't changed since V1. Readable, it's writable, it has random access, it's sync or async, and you pass in the buffer you want to read into. This is immutable, right? But still, we have added a fuck ton of APIs since V1 because the mechanics have changed, right? The way you do async has changed. The way you, like the way that you manage buffers have changed.
We've added some more convenience APIs, but the core APIs that basically everyone can depend on and still use for the most basic implementation, if needed, haven't.
Right, but implementations again, going back to implementations, it's in my opinion, it's close to irrelevant. And the same thing about like finding, a common subset of APIs in several implementations is also not super useful argument, because I can say, well, I took several random types from the framework. The common set of APIs happen to be those two random APIs. Therefore, let's add an abstraction for those two APIs.
Right, but this
doesn't yet prove that the abstraction is useful.
This isn't a random set of APIs. This is the base concept of a primitive tensor type.
I know, but that to me, this whole story was to prove or to illustrate why I think the consumer is so much more important than implementers. The fact that like several types have some common set of APIs says nothing about whether consumers will be able to do with the subset.
Almost everyone who has a producer-consumer pattern where you don't know who the producer is, but you do know who the consumer is. Most modern libraries use some form of interface and dependency injection to solve that issue. They define some kind of marker type that says, I am this. Those marker types sometimes expose some core operations that allow you to interact with the type, even if you don't know the concrete type. And then they use some mechanism to resolve the concrete type at runtime. When you don't want to take a dependency on everything, you use dependency injection or something similar to do that.
So we should implement the consuming code that does exactly what you said, because there's a possibility that the fallback will be, I just want to copy into my vBuffer because I'm not going to re-implement my algorithm 5 times over for this library, this downcast, and then fall back to some APIs that are super inefficient to a point where consumers would basically be disappointed. I'm going to just copy into vBuffer. Well, then we discovered that the actual abstraction that we should have is dense tensor and give me the memory so I can copy it. I don't know. The point is, let's do the experiment. Let's write and let's focus more on the consuming code, not on the implementation.
Well, I think one of the problems is that when you have libraries that have concrete types themselves, so they are the ones implementing the tensor. They're the consumer of iTensor and the producer of iTensor. They're going to be producing a set, and so they're always going to be operating on their type. The point where the interchange becomes useful is when you have a third-party library that is supporting one or more of these external libraries. So, for example, someone like math.net who wants to expose primitive tensor operations that are abstract from any particular library, they end up wrapping the other libraries, and then the application developer can say, oh, I want to support Intel MKL, or I want to support Onyx, or I want to support this. This gives them the ability to provide the primitive support and still exchange and plug in with everything else, because they're not a producer. They are the consumer of the type, providing an abstraction over it. It's the same problem we've had with hardware intrinsics, where they're platform specific, and so people have to write if platform ISA is supported, do this, else software fallback. And people want, and even in our own cases, there's times where you want to provide a set of core operations that abstract the if-else checks from you and just provide a common vector math library.
Let's see the implementation.
I think the scenario you're sketching makes sense to me. I think all we're asking is can we validate that that's the case?
Yes,
and that they actually go through these API shit, is this viable? Because the thing is, with hardware intrinsics, it's a good example, right? We basically said the hardware intrinsics themselves don't have a software fallback. They would just blow up if you use them on the incorrect platform. Because the belief was that that's the wrong granularity. We said these higher level operations like CSC32 or whatever, they may have a software fallback because they have enough instruction that it will be surely not as fast, but it would be still as fast as anybody who would just write naive code, right? Which we think is good enough. Right? And then the code looks reasonable. We know the JIT lights all the things, so the scenario I think is validated. And I think here the only thing we're saying is, are we convinced that this API ship first is the right one, and then are we sure that once we start adding concepts to it, like index and range, that we can evolve them, or can we even get away with basically less API surface, because it turns out the way consumers work is that they either downcast to their own stuff or copy, right?
Well, I
think
would,
that's effectively the
I would
question.
almost say that I think the only argument I would have is if we were to say that the concept here is less and all you want is something like iCopy2, then we shouldn't be exposing a iTensor type at all. We should be exposing an iCopyable interface that allows you to take an arbitrary object and copy it to some other byte storage. That way you can interact with it.
Well, but then you don't know that you can downcast. So Emo said it at some point, that, like, maybe it gets to a point that it's so simple that I actually would stop worrying about this being an interface. And the extreme is a marker. So imagine that we just have iTensor. It's not even generic. It's just iTensor, and it's empty. So you take it. It's basically a promise that it is a tensor. You keep downcasting, and maybe it's not a full marker. It has one method, basically. I try to downcast to several tensors that I know about, and then if not, just give me the memory.
Right.
Right. But the problem then is the same thing we've gone back and forth about, is that getting the memory is not always applicable. If you had a jagged array, then getting the memory is not applicable because you have multiple memories. If you have a sparse, then it's not applicable because there isn't memory per se. You've got some abstract mapping.
Maybe not memory, but copy to vector of t. Like some fallback that actually is reasonable and not going through what I can imagine, like these indexers would be just so horrible.
The indexers make me really nervous as well.
I mean, I'm not sure why, considering that on Sparse.
Well, on Sparse, I mean, what's it going to do? And like on Dense, I mean, you already, like, given that you know that it's dense,
I mean,
you already know the layout. So I don't like these indexers.
On a sparse tensor, if the value doesn't exist, you return whatever that default value is, or the non-existent value moniker is. And then
yes, I know, but I mean that implementation is going to be kind of obnoxious and not something that you'll want to use anyway. And in the dense tensor, you have a better alternative anyway. So what's the purpose of this indexer?
It's a convenience overload specifically for the case where you're just wanting to say, give me the value from this index. I don't care if it's dense or sparse. I just want.
But if it's a convenience, does it belong in the interface, or does it belong in some sort of convenience utility extension method or something like this?
Well, I mean,
I'm not. I don't know. I mean,
indexing is the most basic operation you can do on a tensor.
I know. I'm just sort of wondering.
It's also exposed on every single library that has a tensor concept. Is you can.
But this. I know, but this is sort of like, I think this is getting back to the whole sort of like, looking at the implementers versus looking at the consumer's point of view, right?
I mean, as soon as you want to debug something and you're debugging through your code, you have a local and you want to say, I just want to see the index of this without expanding the IEnumerable view, then this is how you do it. You have an indexer and you say, I want the value from index 1, 2, 3, and the debugger prints it back out.
Another thing to think about, contrast this to Python, where NDArray will take the raw data and let you interact on it. So you can deal with the native multidimensional array type and have it wrap the memory that came from the library, but we don't have that.
Right.
We don't even have an abstraction for a multidimensional array type.
Right. The indexers probably won't be used from a performance-oriented library perspective. They will be used from an interactive user model perspective, where users they're opening up a console window and they're just playing around with tensor types to be like, oh, what happens if I add these two things together? Or what happens if I do this primitive operation? Because they're learning.
And they will
Or a notebook experience.
Yeah.
But they will,
Talking about that other avenues.
but they will have a concrete type. They won't have the interface, correct?
It depends.
Why would they have the interface?
Because they might be using something like math.net, which could conceivably take iTensor, return iTensor, and internally they make the differentiation of, oh, I want to run this against the GPU, so I'm going to use GPU, or I'm going to use Intel MKL because I'm on an Intel CPU and I've got AVX 512 intrinsics available, or hey, I'm on some low-power ARM machine and I just want to do the least efficient thing and iterate over
I
linear.
buy it. It's still a trade-off, correct? Like we are now in like, hey, in the debugger we could have debugger viewers, but you're saying interactive console won't have the APIs, and then we are. We would enable it at the cost of some other trade-off.
It's not a cost of trade-off for anything. Every single type already exposes these operations, so we're just exposing the interface for them. To say, this is a primitive operation on a tensor, sure. You should be able to do this primitive operation even if it's not the efficient thing.
But it's a good example of something like, how much do we care about the params, right? So for example, C#9, they're looking into span-based params, right? The question now is what happens when we do that, right? How we version that interface at that point, right?
Well, changing something to B params is a non-breaking change.
No, it is a breaking change if you implement the interface. Because you put the params there, and so now it's only matching the interface definition.
Which one do I call if I now this and pass five ints?
You cannot have two params. You would have to remove params from the first and you have to add it to the second.
No. C#9 with their params is allowing multiple definitions of params, specifically for backcompat, and the read-only span one is chosen in the new version if you have both.
So that would be a breaking change, because in first version the int version would be called, and then suddenly it would switch to the span version.
If under the hood you have an indexer that is doing something different when it takes an array versus when it takes a span, you're already broken.
No, I mean, I'm saying, so let's say that what you're saying is true. It still means that if we version this library and we silently now add the params marker to the second indexer, you break source code.
No, because the params does not impact method signature resolution. Params is not a modrec. It's just an attribute that the compiler does for magic at compile time.
So you're saying when I implement the interface, I can omit params today, it will just work fine?
You could omit the params. So I don't think C# will let you compile without having the params. So it would be a breaking change on recompilation saying you should add your params here.
Right. So that's.
But it would not be a binary breaking change, and it would be a trivial fix for anyone implementing.
Sure, but that's the same thing with DIMs, right? So like DIMs are, if we do it in the runtime, a non-breaking change for VB, but it's a source breaking change for VB if you recompile potentially, right? Unless we do work. I mean, that's the same example. All I'm saying, that's an example of something that is purely mechanical, has no implication on the shape of the API, but it does implicate like your ability to evolve the thing without breaking downstream consumers, right? So that's what I'm saying. Let's just validate the scenarios.
Yeah.
It might be easier to add these things later. Maybe it's easier for an abstract base type. Maybe it's not. But that's basically it. So I wrote a bunch of notes. Most of them are.
We should add WinML to our list of people.
WinML.
WinML. They have iTensor, right? We might as well be looking at that library.
I need to be back in 40 minutes. So.
That works for me.
But what are we going to do?
Kebab?
We're going to be able to come back? Okay, then, but let's run quickly.
Yep, all right. I hang up, guys. Let me just quickly hang up the YouTube stream as well. Doop, 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 doop.